Good morning. Sound check, sound check. Can someone indicate if you can hear me? Let me see. I haven't muted anybody, so please let me know if you can hear me. Anybody? Students, class reps. Well, I will assume you can hear me. Good afternoon, all. In the last class, we started our introduction to electrochemistry. We defined electrochemistry. Oh, wait. Yeah. We defined electrochemistry, and today we're supposed to talk about electrochemical cells. We started the brief introduction of electrochemical cells by defining some of the important terms we will come across, like electrolyte, salt bridge, and all that. Then we saw an example of an electrochemical cell depicted in this diagram. Now, before we continue, does anyone have any questions on what we've done so far? You were expected to go read up. Are there any questions? No questions? 28 participants. Well, since there are only 28 participants here, I think today, okay, maybe there are more people on. Maybe there are more people on YouTube. Anyway, so in the absence of any questions, we continue. So we've talked about, well, started talking about electrochemical cells, but most of you will be more familiar with the term batteries. Electrochemical cells are usually, or rather batteries are usually a collection of electrochemical cells. Sometimes when it's just one, it's one cell or single cell battery, or if it's more than that. So we've already established that oxidation and reduction occur simultaneously. We've also established that redox reactions will generate electrical current. And that's why we said that chemical energy is converted to electrical energy. And I emphasize that you must, at your own time, look at that and be able to distinguish electrochemical cells from an electrolytical setup. So in electrochemical cells, you have that chemical energy is converted to electrical energy. But in electrolytical setup, or you can also call it cell if you like, the converse is the case, where you have electrical energy being converted to chemical energy. And that's what the process of electrolysis is. You introduce a current, and the current will make the chemicals, the ions decompose at the different electrode, the anode and the cathode. So I emphasize that you must endeavor not to confuse them, especially the electrodes, because the anode and the cathode in electrolysis are swapped in electrochemical cells. I hope you looked at it, but this one that I can't get any questions, I hope you looked at it and you understand it so well that you don't have any questions. I hope it isn't because you haven't looked at it, in which case we will meet in the exam hall. Okay, so second bullet point there says, therefore, the process in galvanic cells. So galvanic cells will also be another name for electrochemical cells. Okay, and you see here, therefore, the process in galvanic cells or electrochemical cells or batteries are the reverse of those in electrolytical cells. Electrolytical cells are where electrolysis occurs. So please try and make that distinction. So what is a battery? A battery is a combination of one. Well, when is one is no combination. So, but the battery has one or more galvanic cells. When is one is called a single cell battery. Okay, and like we said, it converts chemical energy into electrical energy. A single cell battery will contain one galvanic cell. Multiple cell battery will contain more than one galvanic cells. And they are in series. They are usually linked in series. If you remember your physics, you most likely know what it means to link something in series as against linking it in parallel. So a galvanic cell is denoted thus. Remember, we did how to denote a redox couple. Now, this is for a galvanic cell. And remember that for a galvanic cell, just like the diagram we drew here, we said that galvanic cell is the same as electrochemical cell. And this is the diagram. So you can see that it has two different electrolytes connected by a salt bridge. And in each of the electrolytes, you have the electrode. One is the anode and one is the cathode. So to represent them, you take note of all of them. So you usually write the anode first, then you write the anode, the electrolyte in which the anode is, then you draw double slash, then you write the electrolyte in which the cathode is, and then you write the cathode. So if you go back to this diagram here now, you see that this first part, the first beaker on the left, that's the anode. You can see it has the zinc electrode, okay? And the anode electrolyte is the zinc nitrate, okay? Then the salt bridge is represented by two slashes. Just put the two slashes there. And then you move into the next beaker, which is the second electrolyte, copper nitrate. And you can see the copper electrode. So basically how it's arranged here is the convention. You have your anode on the left, you have your cathode on the right. Now, when you want to write it as well, you follow the same convention. The anode first. In that case, the anode was the zinc. The anode electrolyte, in that case, it was the zinc nitrate. You draw the double slash to show the salt bridge, or to show that that is a different electrolyte system. Then you now write the cathode electrolyte, which in that case was the copper nitrate, then another slash, and then the cathode, which in that case was the copper. Okay, so the single vertical lines indicate different phases, but with physical contact. Okay, so the anode is a metal strip, is a solid. The anode electrolyte is a liquid or a molten. Okay, so there are different phases, solid and liquid or solid and molten, but they are in contact. They make contact with each other. Unlike the other electrolyte in the other beaker, you can see it's in a totally different beaker, so they don't make contact at all. The connection they have is that the salt bridge is there. Salt bridge, we've said, is neutral. It will only conduct the ions it will not participate in the reaction. So the double line indicates the salt bridge, a porous divide permitting ion flow while preventing electrolytes from mixing. So look at an example here. A zinc copper cell will be written as this. Now, this diagram is an example of a zinc copper cell because the zinc and the copper are the electrodes. So that's why it's called a zinc copper cell. And you can see the electrolytes in the beaker. Now, if you come here, you see how it's written. So the anode is the zinc. You can see it's solid. The anode electrolyte is the zinc ion. Notice that even though the solution is zinc nitrate, it's the zinc 2+ that is being emphasized because that is really what is involved in the electrochemical reaction. The NO3- you can see is in both places, so you can say they neutralize each other. You remember how we wrote the equation the other time? Is basically the same. No, I think you jumped too fast. Okay, so that's an example. So the Zn2+ aqueous. Okay, so aqueous is used to represent liquid and molten. The molten state and liquid state are both represented with AQ, aqueous. Then you have the double slash, which represents the salt bridge. You can see the salt bridge is not written. It's just represented by 2 strokes because basically it's supposed to be neutral. It doesn't participate. It's just a conduit that will allow ions flow. So whatever chemical is made of is immaterial, so long as that chemical is not participating in the redox reaction or in the electrochemical reaction. So you move to the other electrolytes, the cathode electrolyte, you see again, instead of Cu2+ NO3-, you have Cu2+, also aqueous. Then you have your slash and then the copper solid. So this is how, if you're asked to write a notation or an equation for an electrochemical cell, this is what you are expected to do. So anybody looking at this now, we know that on the left-hand side, the zinc is the electrode and the electrolyte contains zinc ions, Zn2+, while the cathode is copper and the electrolyte for the cathode is a solution containing zinc ions. Any questions? If you have a question, you indicate by a show of hand. Okay. Next slide. In a galvanic, okay, again, we're introducing another name, voltaic. So now you have electrochemical cell, you have galvanic cell, you have voltaic cell. They all mean the same thing. Sometimes you can just have battery. They all mean the same thing. They're all talking about electrochemical cells because chemical energy is converted into electrical energy. So they can be used interchangeably. So you take note of that. You can have galvanic, you can have voltaic, you can also just say electrochemical cells. So in a galvanic or voltaic cell, the cathode is positive, whereas the anode is negative. Now, this is the opposite of what you have in electrolysis. In electrolysis, the cathode is negative. Okay, so maybe to help you, well, that's what the second thing is saying. In contrast, in an electrolytic cell, electrolysis, the cathode is negative and the anode is positive. This can be very confusing. So I restate, reiterate, even make noise about it take note of this, read this very well, make sure you understand it. Because if you don't, and you get to the exam hall, you can get confused. Now, generally, you learned about electrolysis in secondary school. So maybe one way, whatever you learned there will still stick with you. If it does, then all you need to know is that whatever happens in electrolysis or in an electrolytic cell, the opposite is what you get in an electrochemical cell, also known as a galvanic or a voltaic cell. Now, if you don't remember or if you never did it, in electrolysis, the cathode is negative because the cations will go there. Remember that like poles repel, unlike poles attract. So plus and minus will attract, plus plus or minus minus will repel. So if you remember that a cation is plus, then plus will go to where? Negative. So the negative, the electrode has to be negative. And the cation goes to the cathode. So cation plus goes to the cathode, which is minus, because if it's not minus or if it's not negative, it will repel, so it cannot go there. It's because it's negative, that's why it can attract the cation. Okay? And then the reverse is the case for the anode. The anode, anions, which are negatively charged ions, will go to the anode. Anions are negatively charged, so they will go to the anode because the anode is positive. So that ion called anode is positive in electrolysis. Once you can remember it like that, cathode to cation, cation to cathode, C to C, anion to anode, A to A. If you can remember it like that, then you remember that because cation is positive, it will go to the negative. So the cathode is negative. The anion is negative, it will go to the anode, which is positive. Once you have that at the back of your mind for electrolysis, then you just say, when you come to electrochemical cells, the opposite is the case. So in electrochemical cells, the cathode now becomes positive, the anode now becomes negative. Now, if it confuses you again, remember that in electrolysis, electrical is converted to chemical, while in electrochemical, chemical is converted to electrolysis. You made it this far, you're in the university, so that cannot be difficult for you to read, understand, and remember, if you choose to. If you leave it alone and you go and play, and you go and do other things, today is Valentine. Now, many of you are not here. I'm looking at the participants, 50. You can do all the Valentine and forget the rest. Then, when the exam comes, you can answer. Any questions? Does anybody have any question? Okay, no questions. Everybody is busy thinking about their Val and Valentine gift. So we move on. Types of batteries. We've already said that batteries are, you can have single cell, you can have multiple cell, but it's when the galvanic or voltaic cells are connected in series, they will give you a battery. So types of batteries, many of you are familiar with the lead storage battery. Most cars and kekes and korokwes use it. You have zinc dry cell, alkaline dry cell. We're going to look at some of this in detail. Okay, so these are the types of batteries we're going to be looking at. You have one or two newer ones that are not here. If you have a question, you raise up your hand and I will call you. Don't type any question here and ask me. Anyway, you've typed that one, we'll answer it when it's time to answer question. I guess that can work too. Okay. Brief explanations of what batteries are. So a lead storage battery, that's a car battery. It's a typical volt battery. It consists of 6 individual cells connected in series. Now, those of you who have seen batteries, I guess maybe I should have brought a picture here, but I know many of you have seen batteries. Even if you don't have a car or there's no car in your house, your neighbors or other people will have, or you'd have seen people carrying batteries around. It's usually a flat box. I mean, it's like a box, rectangular, and then on top you will see, well, nowadays you don't really see it, but you see 2 ends of something like a metal sticking out. Those would be the electrodes. One is positive, one is negative. So that's a lead storage battery. It's called lead storage because the electrodes are made of lead. Now, this is being discouraged in the current world of sustainability because of lead poisoning. A lot of people use the batteries when they are exhausted or when they are totally discharged. They don't dispose of them properly. So you now have lead getting into the soil. From soil, it enters the water we drink or the plants that we eat, absorb them and pass them to us, or even the animals ingest them as well and pass them to us. And lead poisoning is a very, very serious thing. As little as ppms, as small as micrograms, can affect any human being. You can't see them, you can't taste them, so that's why they're very dangerous, but they can cause a lot of harm. So lead storage batteries are gradually being deactivated or decommissioned. The next one is zinc dry cell. Those of you who grew up in the village, or even if now you see for remote control, for torchlight radios, many of them will use the dry cell. Okay. It's also called the Leclanché cell. Leclanché is a scientist that discovered it. Zinc, again, is the electrode. Usually you see that metal covering the outside of the battery that you see, that's zinc. And then inside you have a paste. Those who have been adventurous enough to ever open a battery. Because usually, growing up those days, some people would take away the rubber top of the battery and cut out the end of the cover of a pen, a biro, and then stick them together and use them to play a game. I think they called it kosa in some languages. But if you've never seen, most of the batteries you see, they use for torch, and they are dry cell batteries, zinc. So that's an example of a dry cell battery. Okay. Then you have the alkaline dry cell. It is a modification of the Leclanchés. Okay. So one of the differences is that the sodium chloride that you would have in the zinc dry cell, sodium chloride, those of you who know sodium chloride, you know that because it can form lattice, it can be solid. Okay, and then if you add a little solvent to it, it will be a paste, but it can conduct ions because you can have NH plus Cl minus. Okay, so that's what you have in the Leclanchés. So, but in the alkaline, the ammonium chloride is now replaced with a base or an alkaline, hence the name alkaline dry cell. So in the alkaline dry cell, you have the paste as containing sodium hydroxide or potassium hydroxide instead of ammonium chloride that you have in the zinc dry cell. So that would be the main difference. All those cells that we've talked about now, the lead, the zinc dry cell, and the alkaline dry cell, are all non-rechargeable. In other words, once they discharge, that is the end of their life cycle. Okay, and I mean, some of you will already know that when you put battery in your torch on your radio, once it dies, you throw it away. Okay, so mercury dry cell is also a type of Leclanche or a modified Leclanche. Okay, so instead of manganese 2 oxide, you now use mercury oxide, and then you use steel as the cathode. The previous one, too, we looked at, you use zinc as the cathode. That's the cathode is the thing that covers it, the metal there. So for mercury dry cell, you use mercury oxide. So that should be easy to remember. Mercury oxide for mercury dry cell. The next one is a nickel cadmium battery. It's also like a Leclanche's, but you are now using nickel as the cathode and then cadmium as the anode. Hence the nickel cadmium name. Okay. You notice that in the mercury dry cell, you are using the mercury oxide as the paste as well as the anode, and then you are using steel as the cathode. But in the nickel cadmium, you have the nickel as the cathode and you have the cadmium as the anode. A possible question, for instance, the nickel cadmium battery, which of the following is the anode? Then you'll be given options: nickel, cadmium, zinc, lead, and you have to choose one. So if it's asking for the cathode and you choose anything other than nickel, that's the wrong answer. And you know what happens to wrong answers? They get to do. So apart from the fact that the cathode and anode are different, you also find that this nickel cadmium battery is rechargeable. So that's the main difference between this and the first four that we've looked at. The lead storage, the zinc dry cell, the mercury dry cell, the alkaline dry cell, they are all non-rechargeable. Once they discharge, or as we say, once they die, or the correct term is discharge. So since you are in school, you use the correct term so that you won't be like an illiterate. Okay, but the nickel cadmium is rechargeable. So what do we mean by rechargeable? The reactions at the anode and the cathode are reversible. So that's what it means in chemical parlance. So as a chemist, the person on the street can be saying rechargeable, rechargeable, and not know. What rechargeability means is basically the reaction is reversible. That means the reactants will give you the product can give you the reactant. Unlike the first four, the reactant will just give you the product. When you write the redox reaction, the half cell reaction, it will just have the arrow pointing in one direction to your right. But for galvanic cells or batteries that are rechargeable, the arrow will be pointing to your left and to your right. So that means that once the reactants combine to form the product can go back to the reactant. That is how they are rechargeable. But obviously, to a limit, they continue to recharge till is the materials there are decomposed. Because as they produce electrical charges, the electrical charges decompose them as well. Okay, another example, which is a modification of the nickel cadmium, which is also rechargeable, is the nickel metal hydride battery, NIMH. In this, the cadmium is replaced because of its toxicity. So the toxic cadmium anode is replaced with a hydrogen atom impregnated with zirconium nickel. Zr is zirconium, Ni is nickel. So ZrNi2 metal alloy. You know what alloys are? When two or more metals are combined together to form one metal. It's usually done to exploit the favorable properties of both metals. So they'll usually be combined for synergistic purposes. So let's say one metal is a good conductor, the other metal is a good absorber. For example, you now bring them together in an alloy, that alloy will be able to conduct and absorb. That's what alloys do. So basically, in the nickel metal hydride battery, the cadmium is replaced. And it's replaced because cadmium is toxic. The same reason why lead batteries are being gradually deactivated, or their use is being gradually discontinued. The last but not the least, the lithium ion battery. This is more recent, and more developments are now based on this. So you see some of them, you use them as solar batteries. See some of them, they use them in computers, as timers in computers. I hope we all know that timers are part of the hardware of a computer. So even when you switch it off, it is there working to keep things going. So a lithium ion battery is the newest rechargeable battery. From the name, you obviously know that it's made up of lithium ion. And it works by the migration of lithium ions from the anode and vice versa. Again, this is reversible. So those are the how many now? 7? Yes, 7 types of batteries. Yeah, 7. And if you look here, you see the way they are listed. In a way, they are listed according to how their development. So lead will be the oldest, lithium will be the newest. Lead is now rechargeable, lithium is rechargeable. So as you move down, you move from better quality, better conduction, durability, and then of course you move towards green or sustainability. And you will be expected to know the differences between these cells or these batteries, especially in terms of their electrolyte, their anode, and their cathode. Any questions? Okay, let's go and see. Someone asked the question on the chat. That's why I say you raise up your hand, because now I have to start looking for. What is this one? Start looking for. Let's put it this way. Start looking for the question. All these people that won't come to class, their own is just to write names. You come to class every day and you don't listen, or you listen and you don't grab anything. You're not helping yourself. But most of you are preoccupied with writing your names first. Where's the question now? Yeah, I think that's probably what I am going to do. Come here. Yes. Someone had a question I can't find it here. So please, if you can raise your hand. Okay, look at it there. So electrolysis is a electrochemical cells. First of all, that is incorrect English. And second of all, that is exactly what I'm telling you it isn't that you are writing here. So it means you are not listening. I'm telling you that electrolysis is the opposite of electrochemical cell. You're asking me. You're lucky I can't see your name here. You would have seen what would have happened to you. Anyway, since I encourage you to ask questions, your question that you have asked shows that everything I've been shouting about, you haven't been listening. So the answer to your question is no. Electrolysis is not electrochemical cell. It is the opposite. Let those who have ears hear. Go and read this thing. Okay, so moving on. Still on electrochemical cells. Standard potentials. So usually, because this is someone asked this question in the last class, and I was saying we're going to deal with it in future. I hope the person is in this class listening, because I can't remember your name. So the standard potential of any galvanic cell is the sum of the standard half cell potential for the oxidation and reduction half cells. That is, E naught cell, which is the standard potential, is equal to E naught oxidation plus E naught reduction. That is self-explanatory because they happen at the same time. So the reduction half cell reaction will generate its own potential. The oxidation half cell reaction will generate its own potential. If you add those two potentials together, you will get the standard potential of the cell in which those reactions are occurring. That's basically what that is saying. So standard half cell potentials are always quoted as a reduction process. Therefore, sign must be changed for the oxidation process. What that means is that, generally speaking, simplistically, you can say you add oxidation potential plus reduction potential, you get the standard potential. But because most of the things involved in this are metals, and metals are reducing, so the whole process is usually taken as a reduction process. So what that means is that if your oxidation process is positively charged, you have to change it to a reduction process by changing the charge. So if it's positively charged as oxidation, it now becomes negatively charged. And if it's negatively charged as oxidation, it now becomes positively charged. I hope that's self-explanatory. The next bullet point, the cell potential, which is the E cell, is also known as the electromotive force, EMF. So you can be asked for cell potential, you can be asked for standard cell potential, you can be asked electromotive force, or you can be asked EMF. The same or different words for the same force or potential. The standard half cell potentials are determined from the difference between the two electrodes. Wait, did I skip something here? Okay, no. Okay. So usually, Tolu, what was the question? Unmute yourself. Tolu, unmute yourself and ask your question.
Yes,
Quickly.
Sir, please, I would like you to please explain this second to the last point on the last slide, sir. That talks about potential and changing of oxidation to reduction, from reduction to oxidation, sir.
What do you want me to explain? I just explained it. Ask a question.
Standard. Okay, sir. Like, I don't understand the reduction process that a sign must be changed.
Do you understand how you were born?
I'm sorry, sir.
Do you understand how you were born? Yes or no?
Yes, I understand, sir.
Okay. I said to you that generally speaking, in a redox reaction, oxidation happens simultaneously with reduction, right?
Yes.
Now, in a standard potential, you are adding the potential of the oxidation with the potential of the reduction.
Yes, sir.
But if you look, you will find out that most of the elements we deal with here are metals. And metals are electropositive. So they are reducing by nature.
Sure.
So in order to factor that in, you say that because oxidation and reduction happen at the same time, and what you're dealing with is a reduction process, anywhere you see oxidation, in order to calculate your potential, your standard potential, anywhere you see oxidation, you now consider it as a reduction process. And the way you consider it as a reduction process is by changing the sign of that potential. So if the oxidation process has a positive sign for the standard potential, in order to use it to calculate the E naught cell, you change that plus to minus. And if it were minus in the first place, in order to substitute it in the equation, you change that minus to plus. That's what I'm saying. Don't worry, you see examples. So before we look at the examples, we want to talk about what standard potentials are, because you know a standard means that you are comparing one thing to a known quantity. You say the standard of measurement of weight is kilogram. You say the standard of measurement is meter. And if you go to some laboratories, central ones in Paris, for instance, you will see the standard there, so that every other one that is made in the world is taken from that standard. So that everything, so if you say 1 meter, you are in Lagos, you say 1 meter, the person in Sokoto will get the same measurement as 1 meter, the person in London will get the same. So that's called standardization. So how do you standardize potential? It's usually by comparing it to the potential of hydrogen gas. Okay, so this slide here, first of all, tells us that the standard half cell potential are determined from the difference between two electrodes. We already know that, one anode and one cathode. If, just like you say, if you don't have a positive and a negative, you cannot have electric current. So that's why you say you have to make contact. The positive and negative have to be connected before you can have any form of current. So the two electrodes here are the anode and the cathode. The standard hydrogen electrode, She, is the reference point. So if you want to get the standard potential of any other metal, you compare it to the standard potential of the hydrogen electrode. And mind you, hydrogen is a gas. So just for you to have an idea of what is going on there. But that is the potential you use to compare, to get the values. So these values are usually known. They've already been determined experimentally. So if you need to do any calculations that require this, they will be given to you. So you don't need to cram them, but you just have to understand what they are, how they are derived, and so on. But you don't have to cram the values. Okay? So the standard hydrogen electrode consists of a platinum electrode in contact with hydrogen gas. The hydrogen gas will be at 1 atmospheric pressure with aqueous hydrogen ions that will be in a solution that is of 1 molarity. So where you have a cell that has a platinum electrode immersed in hydrogen gas, and that hydrogen gas is at 1 atmospheric pressure with 1 molar H ion solution. That is what you would describe as a standard hydrogen electrode. SHE or SHE for acronym. And that standard hydrogen electrode has been assigned the arbitrary value of 0 at all temperatures. So what you now do is, if you want the standard potential of copper, for instance, you compare it to that of the hydrogen to give you a value. It can be plus or minus. It can be above. It can be on top or under. That will then give you the value. So this is how the standard potentials of all the elements you've been seeing are derived. And here is a diagram of how these things were derived. You have no business doing this. Chemists have done them already, and they've determined the value. So if new elements are discovered, for instance, they will go and do. This one is not your business, except you decide that in the future you want to go, when you finish your first degree, you go do masters, do PhD, and specialize in this area of analytics. Then that's when you worry about it. But now it suffices for you to know that this is a diagram of how the standard hydrogen electrode potential is determined. Again, you can see that there are 2 different beakers. You have a salt bridge. You can see that there are 2 different electrodes. Okay, and you can also see that the electrolytes and their constituents. So the knot in the E knot indicates standard conditions at 25 degrees centigrade, 1 atmospheric pressure, and 1 molar for the temperature, pressure, and molarity of solution respectively. This is just for your information. Okay. Now, if you quickly go to this slide here, now you will see the standard reduction potentials. So if you look here, these are all reaction, reduction, half reaction. You see? You see, that's why this is called the reduction potential. It's basically talking about reduction. All of them are gaining electrons. Electron gain is reduction. And this is one of the reasons what it is meant when they say that you're going to consider it as a reduction process. Okay, so we're going to come back to this later, and you can see their values here already determined. These are the E knots for all of this. So if you take hydrogen peroxide, for instance, second line, 1.7, and then you'll also notice that as you go up from the lower one, as you go up, you are going to be meeting stronger oxidizing agents. And then as you go down, you're going to be meeting stronger reducing agents. We already know what reducing agents are. Okay, so let's look at some examples. Any questions so far? Does anybody have any questions? No questions. Okay, so let's go and look at some examples. Now look at this. Zinc metal in dilute acid gives hydrogen gas. We already know that. When we already know what She is, standard hydrogen electrode, is connected to a galvanic cell with zinc ion, zinc solid electrode, a spontaneous cell process is obtained. This is just an example of a question that you can come across. So you see the oxidation process here, everything is given to you. In some cases, you'll be required to, for instance, even determine by yourself which one is the oxidation process, which one is the reduction process. So that's why you have to understand what oxidation is in terms of oxidation number, in terms of electron loss or electron gain. Anyway, here, the oxidation process, see the equation there, zinc solid, we give you the zinc ion plus electrons. Okay, so in this case, the zinc is losing 2 electrons to give you the zinc ion. Electron loss is oxidation. In the reduction step, you have the proton or the H plus gaining 2 electrons to give you the hydrogen gas. Okay, now the E0 cell is 0.763 volts. 0.763 volts is the same thing as plus 0.76. So if there's nothing written in front of the numbers, you assume that it is positive. If there's something written in front, which is the negative, you know that it is negative. Okay? Now look at this. Remember that hydrogen is the standard. So that means that in this case, it is the E0 of the zinc that is being determined. Now, the zinc is the oxidation process. So that means for you to use it, if you want to calculate the E0 of a cell, okay, let's not move too far. Let's just, so here we're determining the standard of the zinc. The zinc is the oxidation process. So the value is going to give you is 0.763. Okay, and you can see how it has been written, the E0. Okay, now we say that oxidation processes we will consider as reduction process and then change the sign. So here now you can see that the E0 cell is 0.763. Because it's an oxidation process, to use it, as you see in the future, well, you're going to see where we're using it, you have to change the plus sign to a negative sign. So this thing written in red here, E0 Z2 plus Z is, who is it? Excuse me, please. Who is it? You are in the wrong office. Go away. Go away. So you now change the sign to minus. So in your calculation, you're not going to use 0.763. You're going to use minus 0.763. You're going to see how that is important very soon. So now look at this. Again, this is a She for copper. Again, remember, wherever you see a metal being compared to hydrogen gas, you know that that is how the E0 cell is obtained. So here, the anode in this case is the hydrogen gas. You can see that the hydrogen gas in this case loses 2 electrons in order to then give you the hydrogen ion and that. Okay? And then look at the E0 cell. It is plus 0.337. So it can either be written as plus 0.337 volts, or it can be written as 0.337 volts. V is volts. Okay? So here now, it is for the copper. Now, if you look, the copper is a reduction process. So that means that you do not have to, it's already a reduction process, so you do not have to alter the sign. So that's why in this case, the plus 0.337 is what you're going to use in your calculation. Now let's move to the next slide. Look at an example here. here, the more negative value forms the oxidation half cell. Again, this is explaining to you where you have, in this case now, you have silver and zinc as your electrode. If you go and look at the reduction potential table that we looked at just now, you see, now look at silver. See where silver is here? This is silver Ag plus 0.8. Okay, now let's find zinc. You will see that zinc will be lower. See zinc here is lower. Okay, down here, and it's minus 0.7. And look at this arrow. It says as you go down, it becomes a stronger reducing agent. So that means that zinc is a stronger reducing agent than silver. So that's basically what this is telling you here, that the more negative value will now form the oxidation, because the reducing agent is the one that undergoes oxidation, and the oxidizing agent is the one that undergoes reduction, while it is oxidizing the one that undergoes oxidation. If you've read the note, you will understand what I'm saying. And if you don't, please go and read it. So basically, the more negative here is the one that will be the oxidation. And since it's the one that is the oxidation, is the one that you will change the sign. So in these two equations that you have here, see the first one, zinc, you see 0.8, you see, silver, 0.8, zinc, minus 0.6. So zinc, because it's the more negative of the two, is the one that will be the oxidation half cell. So that means that all these things are how you will know, because some questions might not give you all this. So first of all, from here, whenever any metal or any compound is compared to the hydrogen gas is the standard. So you know that that is done to get the standard potential of that compound that is being compared to the hydrogen gas. Okay, and then remember that electron loss is oxidation. Oil rig, oxidation is loss. Reduction is gain. So electron loss is oxidation. If you look at this equation here, Zn solid to give you Zn2 plus 2E minus, the oxidation state of Zn solid is 0. But the oxidation state of Zn2 plus is 2 plus, Zn2 plus, yes, is 2. Okay, so from 0 to 2, there's increase in oxidation number. That's oxidation. Or Zn is a neutral compound. The protons are equal to the electrons. But Zn2 plus means that 2 electrons have been removed. That's why there's a net charge of 2. So before, the electrons and protons were equal, the plus and negative were equal. Now, when you remove 2 negatives, you will now have 2 positives in excess. And that's why you have 2 plus there. Now, because you've removed 2 negatives, it means you have removed 2 electrons. It means that zinc, in moving from zinc to zinc ion, has lost 2 electrons. Electron loss is what? Electron loss is oxidation. So that's how you know that that is an oxidation process. Okay, when you are comparing them. Another way you can know is when you now have 2 metals, when there's no hydrogen involved, then you know that you are no longer standardizing it. You're just looking at the metals themselves. Now, when you're now looking at the metals or the compound, they already have their E0 values. Those will be given to you. So what you now need to do is to look at those E0 values and find the one that is more negative of the two. You look at the values. The one that is more negative. That one that is more negative is the one that you now assume to be the oxidation process. That is now the one you will assume to be electron loss. That is now the one you will assume to be gain or increase in oxidation number. So once you identify that that is the oxidation process, whatever sign is in front of it, you will change it in order to fall in line with the oxidation, with the reduction process. I repeat that. First of all, you identify the one that has, or rather, the one that is more negative out of the two values. Once you identify the one that is more negative out of the two values, that one will be the oxidation process. The other one will therefore automatically become the reduction process. Now you have a reduction process, you have oxidation process. If you now want to calculate the E0 of that cell, what you have are the E0 of the half cells, oxidation half cell and reduction half cell. If you now want to calculate the E0 of that whole cell, the redox reaction, you will now first of all determine which one is more negative. That one will now be the oxidation step. Once you identify it as the oxidation step, you are now going to put the values in the E0 is equal to E0 oxidation plus E0 reduction. The value you are going to put for the E0 oxidation, whatever it is, you change it. So if it is plus 0.1, you change it to minus 0.1 before you put it in that equation and then do your calculation. You must change it before you put it, not after. And it must be the oxidation step that you are changing. I'm emphasizing these things now. It might sound like I'm sounding like a broken record, but if you miss any of these things, you cannot get the answer correctly. So please, at your own time, go again and look at this again. So here in this example, we've identified that the Zn plus 2E to Zn solid is the oxidation process because it has more negative value out of the two values of the E0s that are here. So because it's the oxidation process, we are now going to change it to positive. So instead of minus 0.76, it will now be plus 0.76 before we now come and put it in the equation. This equation here, E0 cell, okay? So you see the reduction process there, the silver 0.08, it doesn't change. This is another example. So you can look at this at your own private time, see the example there and see how it has been used here. Okay? See you on Friday. If you have any questions, bring them on Friday. Our time is up.